The divergence theorem is the second of our integral theorems that we're going to see in this chapter, and it states that if we are going to do the double integral over the surface of f dot in ds, now that was our flux integral that we saw a couple of sections ago, that's actually equal to the triple integral over a volume that we're going to call Q of the divergence of the field dV. So we're going to integrate the divergence across the entire volume to find out what this flux integral is. So just like before, this gives us another option on how to do this integral. One side might be easier to do than the other. Now a few things. Here your surface is a closed surface. That means it encloses a volume, and the normal vector n is outward. Now we talked about normal vectors orientation a couple of sections ago, and we saw that we had an upward facing normal and a downward facing normal. But of course, if we have some volume, I'm just going to draw an easy sphere here. The outward normal is any normal that's pointing, out of the volume. So those are two things that happen. The surface has to be enclosing some volume, and that's our volume Q here that we're talking about. And we're going to integrate across that. So let's see if we can prove this theorem. That means we're going to do two sides. That's why we got part one again. So let's get this out of here and come up with an example. Let's say that we want to find the surface integral of f dot in ds, where f is the field x, y squared, z, and the surface is 2x, 2y, z is equal to 6. And of course, like always when we do these, this will be in a first octant. So always helpful to do a quick little sketch here just so we can get an idea of what's happening. So y and z. All right, so let's see, as we cross each one of these, let's see, x on the x-axis, x will be 3, 1, 2, 3. On the y-axis, y will be 3, and on the z-axis, we'd be up here at 6. Okay, so we get this triangular region here. Now, since we're talking about it's in the first octant, these quadrant planes are also part of the volume. So here, this surface is actually made up of 4 different pieces. The triangular piece, kind of 2 back sides and the bottom sides. So if we're going to do this integral, this flux integral of f dot n ds, we actually have to do 4 of them. We have to do a surface integral for each one of those, and then of course add them up. So let's label these. Let's call the bottom one S1, that side S2, the back side over here S3, and then the actual triangular surface S4. All right, so for each one of these, we're going to have to do the integral of f dot n ds, and we'll kind of do them one at a time over here. So let's take a look at what I called surface 1. All right, surface 1 is basically our xy plane. So the equation of our xy plane is z is equal to 0. So that's the definition of the surface that we're going to do this on. We also need the normal vector there to do f dot n. So if we're thinking about the xy plane and we need an outward normal, it would actually be the vector pointing straight down. So our normal vector here would be 0, 0, -1, because it's got to point straight down out of our volume here. All right, so on surface 1, what is our field? Well, we know our field was x, y squared, z, and when we're on that surface, z is 0, so our field is x, y squared, 0. So when we go to set this up and we're going to integrate across this surface of f dot n ds, I'm going to skip finding ds for right now, because watch what happens for this particular one when we do f dot n. Well, f dot n is x, y squared, 0, dotted with 0, 0, -1, 0, 0, 0. So this is just the double integral over the surface of 0 ds, which is, well, 0. So the value for our first flux through the surface 1 is 0. So we'll put that to the side somewhere, kind of remember that, and we'll get back to that in a second. All right, let's take a look for surface 2. All right, so let's see, for surface 2, that's kind of the back side over there. Surface 2, the equation for that, that's the YZ plane. So the equation for that surface is x equals 0. The normal vector has to be the outward facing normal, which means it's going to have to point back out that way. So that's going to be in the negative x direction. So our normal vector here would be -1, 0, 0. And our field, while we're on that surface, well, we know according to that surface, x is 0. So the field would be 0, y squared, and z. Again, when we go to set up our integral over the surface of f dot n ds, again, I'm going to leave off figuring out what ds here is, because I can already see, just by looking at that, f dot n is going to give me basically the same result we had last time, dotted with -1, 0, 0. Of course, that's 0, 0, 0. So the integral over that surface of f dot n ds, again, is 0. Okay, so that's the flux through surface 2 is also 0 here, so this is working out pretty nice. Let's take a look at surface 3. Guess what's going to happen? Let's find out. For surface 3 is the xz plane. So on the xz plane, the equation of that is y is equal to 0. So we need the outward facing normal. The outward facing normal has to point out of the volume here, which is going to be in the negative y direction. So our normal vector, 0, -1, 0. And when we're on surface 3, our field is going to be x, 0 squared, and z. As you can kind of see, the same result's going to happen for this one. It's a nice example to do. When we integrate across the surface of f dot n ds, well, f dot n again, x, 0, z dotted with 0, -1, 0 gives us, and I'm just going to skip to the chase there, of course, 0 again. So our integral over the surface for surface 3 is also 0. So we've done 3 flux integrals so far, very simple ones, and we got 0 for all of those. So we need to do the surface integral for surface 4. That one's going to be a little bit more difficult because it's a more complicated surface. All right, I'm actually going to go back this way a little bit. Get all this out of here. I'll write our surface back up here in a second. Okay, so we know for S4, our surface was 2x, 2y, z is equal to 6. So we need to solve this for one of the variables. And again, this was a choice that we saw with our surface integrals the other day. Of course, the easiest thing to solve for here would be z, 2x minus 2y. So what would the normal vector on this surface be? Well, this is one that we just can't look at. We know the normal vector here is del G over the magnitude of del G. Now, we got to determine which way to define G here, because remember, to do the divergence theorem, we need the outward facing normal. So if you kind of think about this triangle as kind of sloped like this, you can see that we would need the normal to be pointing kind of upward right here. So to define big G, we need to move everything to the side that keeps the Z component positive. So by definition, we're going to say big G is move everything to one side. We get 2x, 2y plus z minus 6. All right, so to find our normal vector, that's going to be del G. Well, the gradient of G here is 2, 2, and 1 over the magnitude of that, 2 squared, and 1. So our normal vector here is, that's going to be the square root of 4, 8, 9. So that's going to be 1/3, 2, 2, 1. All right, so we found our normal vector. We also need to figure out what ds is this time, because our dot product this time is not going to be 0, because you can see our field on this surface, our field was x, y squared, z. So on S4, just like we did before, our field's going to be x, y squared, and we said z was 6 minus 2x minus 2y. And you can just see really quick that the dot product there is not going to give us a 0, so we're actually going to have to go through this. All right, so we need ds. Remember, ds, a small piece of the surface area, is the 1 plus little g sub x squared plus little g sub y squared across our area, where, of course, I use x's and y's because we solve for z in terms of x's and y's. Little g is the definition of the surface. So in this case, d sub s is going to be the square root of 1 plus, so this is our function g here, this is our surface definition. The partial of this with respect to x is -2. The partial of that with respect to y is -2. And of course our dA here, since we solve for x's and y's, this is going to be dx dy or dy dx. So you can see a small piece of our surface is 3 dA. All right, let's set this up over here, and then we might have to go back over there to eventually finish it. Remember what we're trying to do? We're trying to do the integral across the surface of f dot n ds, this flux integral. So we'll set up the bounds in a second, so I'm going to leave s there. F is, well, f when we're on this surface is x y squared 6 minus 2x minus 2y, dotted with n. On this surface, n is 1/3 of 2 to 1 ds, and ds is 3 dA. 1/3 and the 3 cancel, and we'll, oh, sorry, this is a region now, because we're going across the area. All right, when we, the 1/3 and 3 cancel, when we do the dot product, we're going to get 2x, 2y squared, minus 6 minus 2x minus 2y dA. Still across our region, so we're going to do double integral across our region of, let's simplify this. What do we get? We get 2y squared minus 2y, and the x's cancel, minus 6 dA. Okay, now what is the region that we're talking about? So we need to go back to our original picture here. Since we've decided to define our function as z as a function of x and y, our region is the projection down into the xy plane. So a quick little sketch over here. If we project that down into the xy plane, that's the multiple 3, 1, 2, 3, 1, 2, 3. Okay, so this is our region R that we need to integrate across. And of course, the equation of the line right there is this, if we let z be equal to 0. So that's 2x plus 2y is equal to 6, or of course, x plus y is equal to 6. All right, so we need to determine which way that we want to integrate this. We can integrate either dy dx or dx dy. I got to come back over here because we need a lot more room. All right, so once we've determined which way we want to integrate dx dy or dy dx, there's really not a bad choice here, but kind of think about it like this. If I do dy dx first, by the way, it's still a lot of work either way. If I do dy dx first, y is going to run from 0 to 6 minus x. Then I'm going to have to put 6 minus x into these powers, which is going to be a cubed and a squared, and that's going to be a lot of messy work. So what I'm going to do is I'm actually going to do dx dy. It's not going to be that much easier though. All right, so you'll notice a weird cut here because as I was working through this, I made two kind of really small mistakes that screwed up the whole problem. When we did f dot n ds, that should have been a plus right there. When I copied it negative. And this was the equation of the line that we went through there, which should have been x plus y equals 3, not x plus y equals 6. So I didn't divide the 6 by that. So let's set up this region again, and everything I said before about which order we want to do it's still the same. This would be a lot easier to do. Let's see, we got 2x squared minus 2y plus 6 dA. If we do this dx dy. So if this is our region R, x goes from x equals 0 over to that line, and on that line, x is equal to 3 minus y. And then of course, when that collapses into the y direction, y goes from 0 to 3. All right, so let's go ahead and integrate this. A lot of arithmetic ahead. So we go 0 to 3, this is going to be 2xy squared minus 2xy plus 6x evaluated from 0 to 3 minus y dy. So the integral from 0 to 3 of 3 minus y times y squared 2 times 3 minus y times y plus 6, 3 minus y dy. Okay, right, so everywhere there's an x, we put our 3 minus y. So let's go ahead and distribute this. Let's get this out of the way. All right, so this is going to give us the integral from 0 to 3. So when we distribute this, we're distributing a 2y squared. So that gives me a 6y squared minus 2y cubed. Here we're distributing a negative 2y, so that gives me a negative 6y plus 2y squared. Now here we're just distributing a 6, so that gives me 18 minus 6y dy. So the integral from 0 to 3, negative 2y cubed, we have 6y squared, 2y squared is 8y squared. Negative 6x, negative 6x, that's negative 12y's and an 18. All right, integrating this, we get negative 1/2 y to the 4th plus 8/3 y cubed minus 6y squared plus 18y evaluated from 0 to 3. All right, top endpoint minus the bottom endpoint, we have 1/2 3 to the 4th, 8/3 3 cubed, 6 times 3 squared, 18 times 3 minus, of course they all have a factor of y, so when we plug in the 0, we get 0. So this is negative 81/2 plus, one of the 3's cancel here, so that's 8 times 9, which is what, 72. This is 6 times 9, which is 54, and 3 18s is also 54. Our 54's cancel, we need a common denominator, so this is negative 81/2 plus 144/2, which, yep, that is 63/2. All right, so notice doing these surface integrals for this one was a lot of work. In fact, as you see, even I made a silly mistake along the way and can really throw off everything, so you gotta be careful for each one. Now, we're not quite done yet. We got to put all this together. Remember what we were trying to do? I'll bring it back over here. We were trying to evaluate the integral of f dot n ds for this volume, for every surface on the volume. So the integral for s is going to be the surface integral for S1, surface integral for S2, the surface integral for S3, and the surface integral for S4. So our entire answer, the integral across the entire surface of f dot n ds, is 0 plus 0 plus 0 plus 63/2, or just, I'll just write down here, 63/2. All right, so once you find all your surface integrals, your flux integrals across each surface, add them all up, and that will give you the total flux through that volume.